So, we talked a lot about the principle of architectures, and now in this session we want to show, if you have behavior-based architectures, what are the most dominant behavior-based architectures, and we go a little bit deeper into that, how that actually looks like for real robot systems. So, the one that is reoccurrent everywhere is that you use finite state machines to build up your behavior. So your behavior is the foraging, and you create it by combining a number of finite state machines that send events to each other when something happens, and you make a state change, and then you change how the robot behaves. You can use finite state horizontal or vertical. In behavior-based robotics, we mainly use it vertical, but you see that there are many crosslinks also vertically. So the most dominant architecture is the one from Rodney Brooks. That's a competitive architecture. In chapter 4, a number of architectures, I believe a number 10 of them are defined, and each of them are classified based on this criteria. So, in principle, it's a reactive architecture, so you have direct coupling between sensing and actuation. It was inspired by the Breitenberg vehicles and by the cybernetics. The design method is experimental, bottom-up. Rodney Brooks was the developer, and that's the one that really gets rich with it, because he's the one that created the Roomba robot that cleans up the most houses. But he also created the co-robot Baxter, and yeah, let's say this company that went bankrupt last month. How are the responses coded? That's with a formal logic. So you have a rule-based set, and you decide discrete to do this or that. But it's a very easy way to do, and also currently in Python, say that's how we learn everybody to program with cases, switch cases. What's nicely done is that coordination is competitive. You have a number of vertical layers, and in principle, the higher layers overrule the lower layers. The only thing what is made sure is that there's a timestamp on it, so the taking over is only temporary. And Rodney Brooks first started by augmented finite state machines, but later on extended that to a behavior language, what's say an extended version of the augmented finite state machines. And this is a great architecture because this is the one that is tested on the widest variety of different robots, walking robots, flying robots, all sort of robots have fielded the subsumption architecture. So the building block of this architecture is the behavioral module. The original was this was the augmented finite state machine. And in principle, you have a module. It builds up some history, so you can reset it by a trigger to an initial state. It has some input and output. And you see there the black box approach of the cybernetics coming back. And what is special, that on those input and output signals, you can put inhibitors on the input and suppressions on the output. And in that way, you can other behaviors can control the flow of the behavioral modules. And with those building blocks, you can build architectures where you can see different layers. This is the breakout behavior, and for a cockroach type of robot. And you see 3 layers, each with a connected module, behavior module. So, how is the coordination done in the subsystem architecture? By 2 ways, by inhibition of the input signals. So if you don't get the signal that there is something in front of you, you cannot be afraid of it. Or you can overrule the suppression, and that's the same if you have your driver lessons, that somebody sits next to you, and if you're going to collide with somebody on a crossing, then he just pulls the steers for you and with it puts you on a different trajectory. So it results in an arbitration where only one pipeline through the whole architecture is in control, and that's based on the priority, and the priority is the higher level in principle takes the control over the lower layers. So how do you create such an architecture? By first thinking about what sort of behaviors you need to fulfill the task, then try to decompose that and specify the independent behaviors that a robot should show. Determine what is a good balance between granularity that you are building, that each block is more or less the same size, and then start from the bottom up to create your behaviors for both your sensors and your actuators. And that's demonstrated on different sort of robots. You have the robot herd that could together clean up the office, and that they did together. And here you see a sample of how the robots follow each other. There's a full link with it of this video downstairs. This is the best resolution you could get in those days, so better cameras we didn't have. It's not the compression that you see. So you can evaluate this architecture on the different criteria that we have shown. What's nice is that this directly can be compiled on hardware. If you could run this on the systems in the 80s, then you can for sure run it in your systems now in this century. It has a native support for parallelism. The nice thing is that in the first robot that Rodney Brooks worked, he didn't have enough computing power. So actually part of the wires between the behaviors were actually real wires from computer 1 to computer 2 to get that working. And it can really show really sophisticated behavior for a specific niche. So you could really train it to get really a robot that would survive in that environment. The problem of this architecture is that once it's working and you go from one environment to another one, then you have to do the training of the network completely from scratch. So you don't have that much flexibility to adjust the behavior during runtime. You control everything hardwired, so in how the network is controlled, but also in all the parameters. So if you want a different behavior, you start tuning the timings, etc., etc. So there's not really a good design principle for that. And because you have to the limited flexibility and the hardware control, it's really difficult to reuse elements again for other circumstances. The only thing what you take over once you have done it for one robot in one environment and another robot in another environment, the third time the engineer knows how to do it and can do it much faster. But say this is the complete set of robots where this architecture is tested on, and no other architecture can claim such a wide variety of testing of its architecture, if it works or not. One related architecture that was inspired by the subsumption is the colony architecture. That was John Connell. It was a PhD of student of Rodney Brooks. He took it to IBM, and he would further worked it out. And what he did was that he didn't use the inhibition, but only suppression. So he didn't. He gave all the central information to all behavior modules, but he only would start tuning on the control that they had, and that worked as good. Only it was tested on less robots. So we're going to a different way of controlling, and that's not discrete but continuously, and that's where you start to use potential fields to control the robot. And that's great, because there you can very natural work with potentials to steer your robot along obstacles, because you get the flow of information is also the flow of how the robot could go yes or no through the between two robots, because there are no local minima. So an example of an architecture that's based on those potential fields is the architecture of RBEEP. He with it is the one that wrote the the preface of this. Of this book. Where are we? And this is one that is, say, the biggest counterpart against the subsumption architecture. What's the main difference? In subsumption architecture, you have the discrete way of saying what to do. In the motor schemas, you have the continuous part. What's also really a big difference is that the schema theory is more cognitive. What that means is that the schemas are representing certain objects in the world. For instance, a table or a chair. And what is essential of the schema theory is that once you have seen one table, you know how it looks like. If you see another table, you learn more and more about the variety of tables you can see. Some with a white cover, other with a brown cover, etc., etc. And how more tables you see, how better you get in learning to recognize the table. So every time you see a new table, a new instance is fired, you get all the experience of all previous tables you ever seen, and you learn for this specific table what the characteristics are about, say, color, the number of legs, etc., etc. So in principle, every object that a robot encounters is a specific instance, but also makes use of all the previous encounters that you've seen. So that is, there is a little bit more knowledge in it, but it's not pure knowledge. It's experience and learning what to do with tables. So it's also operational knowledge. So, but what's the big difference? That the building blocks of the motor schemas are factors, and that means that it is possible to do a cooperative coordination to a superposition. And that means that you can build different hierarchies. In some parts, you can say if I want this set and then the next set, so that's sequencing. But also inside, you can do the cooperation and the arbitration. So that's great. What's the background? Aura is something that we will see later on as a hybrid architecture, but the lower level is based on motor schemas. It's really the design method is more from methodology. The designer is Arkin, the writer of this book, and the representation of the controls are based on potential fields, and the coordination is by superposition of all those factors that are suggested, and the programming is done not purely by building blocks, but by combining libraries. So how does that look like? Is you have a number of schemas that correspond to a certain concept in the world. Once one table and two chairs are seen, you get instances for that. They are coupled with motor schemas. So in principle, in case of tables and chairs, you assume that you want to evade them. So an obstacle avoidance schema is started. And all those different parts are combined in subsumption. And you see some of those percepts are used multiple times in different motor schemas. And each of those motor schemas has a certain potential fields. So you can recognize an avoidance field, but also a stay in the middle of the corridor field. And if you sum them up, you can get quite complex behaviors. And you not only can do that in 2D, but also in 3D. And you don't have to calculate the whole field, but only for, say, the current path. And that works quite fine. If suddenly an obstacle pops up in front of you, then you can add that obstacle in the field and plan a path around it. One of the critics that are given is if you have local minima, that you get that stuck in a corner, but by adding a behavior that doesn't want to be on the same place, then you are starting to evade places where you are attracted to all the time, and then you can evade those local minima quite easily. So, how do you design such a motor schema? It's first you start the type of motor behaviors that you need. Then you build the most primitive level based on biological examples. Then you start to make modules that express reactions. You test that in simulation. Once that works, then you test them on the real system. In the reactions, you need certain symbols, certain concepts, and you need percepts for that. So you start to build percepts that are only providing the information that you need. So you don't need to know what the color of the wall is. You only need that there is a wall. So you make sure that you only provide the percepts that you need, and then build a perceptual scheme to provide that, and then integrate all that, test it, and start the iteration again for more complex behaviors. And if you want to do the same example as shown before for the behavior-based, then you see that you can do the foraging by combining three schemas that for themselves are cooperative, but you execute them one by one after each other. So, advantages also the motor schemas support parallelism. You can far easily tune them in real time. You have a clear design scheme how you should do the development, so it's not all in the head of the engineer. And you have also the clear support of modularity. What's the disadvantage? It's less, say, specialized in learning a specific niche, and it all starts with the motor schemas that are designed for a certain robot. So once you have another robot, you should start from the ground up. You cannot actually reuse it very easily for other robots. Still, the schema based is the architecture that's tested on after subsumption on the most robotic platforms. So Arkin have shown that it works really good. So in that sense, the subsumption architecture and the schema-based robotics architectures are the two main players. You have many with it other architectures. There are much more in the book. I will only highlight one of them. That is Dawn. So that is also a subsumption with it architecture, but a really fine with it grained one. And here the coding is a little bit differently. It's not discrete, but it's based on voting sets. So if we go to this architecture, you see that all the behaviors in the downside are parallel executing commands. They all do a voting, and on the end you have an arbiter, and the arbiter is more, say, democratic. So it counts all the votes from all the different modules and then decides which control goes to the controller. And this was tested on this Jeep that drove in the woods and the snow. You see a huge with it laser scanner on it. Currently we have it's far with it smaller. And on the right you see different trajectories that are possible, and all modules vote if you should go straight through, or slowly to the right, or slow to the left, or full to the left, or full to the right. And that worked great. The nice detail of this robot is that it sometimes needs to do some mapping. So they asked the driver to make a full turn with this robot. So if you do that in snow, then you get a lot of piles to do every time turn this robot a full 360 degrees. Okay, that's what I wanted to show on samples. There are much more with it in the book. But what I wanted to show is that if when building an architecture, you have a task and you start analyzing that and decomposing it. On the same time, you have your building blocks and you put them together in a synthesis process, and you should come somewhere together in the middle. So you have a top-down approach and a bottom-up approach, and both work. but you make sure that you meet in the middle. An architecture is about reusing. So it's great that if you have building blocks that are domain independent, but it means that it also cannot learn and specific things from of a domain. So that collides against how relevant it is for a certain domain. On the end, it's the difference between if you have a machine that shows intelligent behavior or that you really understand how that intelligence is created. But we will go a little bit deeper into that in chapter 10 of the book. So, the lessons learned, the behavior libraries are with it very usable to not to reinvent the wheel. To have a good library, you have the right granularity of the building blocks. You can choose for each of those building blocks how you combine them and how you make sure that the coordination works, because every behavior makes a suggestion, and on the end you may have to make a decision. Reuse is always a goal, but not many people have shown that it is actually possible to reuse it. A lot of people started from scratch again. But it's really important to understand what are the basics, so that you, if you decide to start from scratch, that you at least make an informed choice. A lot of architectures are suggested, but not all of them are based on what is known from nature. So it would be we could still gain a lot from biology and neuroscience. Okay, that was it for this chapter. I hope to see you next time.